All right, now we're going to understand work-energy theorem. Unlike any other mathematical theorem, this work-energy theorem is quite interesting because it relates the work with the change in the kinetic energy, So this theorem says that whenever we do work by a certain force that produces a displacement, and that work is actual change in the kinetic energy. So this theorem is quite interesting and easy also to understand. So if it is a theorem, that means we need to prove this. So here it is the proof. Suppose there is a body. Consider the body of the body is having a mass m. Okay, and this body is moving with a velocity u. And when I applied a force F, the body started moving in the same direction where the force is applied and produce a displacement S. After displacement S, the velocity of the body becomes V in a certain time, suppose in the time t, it may be, doesn't matter. Okay, now if I'll prove that the kinetic energy of this position A and the kinetic energy of the position B, which is actually the B minus A, will be equals to work done. So let's try to prove this one. Now we know work done in this case, what will happen? Force is acting and it's producing in displacement in the same direction. So it will be cos 0 degree. So work done over here will be Fs. Now we will keep this equation A. Okay, now we know if the force is acting on this body and it is changing the velocity, and whenever we know the velocity changes, that means acceleration is applied. Either acceleration increase the velocity or decrease. We call it retardations. So here the acceleration is applied and the body is having mass m. So when the acceleration applied on a body mass m, so we call it force. That means a force acting on a body. Okay, so this means a force acting on a body. We will give this equation 1. Second, you can see it is changing the displacement, creating certain displacement and changing the velocity. So from the linear equation of motion, we know linear equation of motion, we know final velocity, square of final velocity is equals to square of initial velocity plus 2 times of acceleration and displacement. So from this equation we can find the displacement will be v square minus u square upon 2a, and this will be the equation number 2. Now I'm going to put this equation 1 and 2, equation 1 and equation 2 in equation A. Okay, after putting these value, we can write work will be force. The value is ma, and s we can write v square minus u square upon 2a, and we can cut down this. Now we can write this half m v square u square. Okay, and we can write half m v square half m u square, which is work done. Now you can see over here this equation is coming. Let's see a little bit. Here this body at the position A, if it is having u velocity, so that means the kinetic energy of this body over here will be half mu square, which is initial kinetic energy before applying the force. Suppose it is ki. Okay, and now after applying a force and producing displacement s, the velocity becomes v. That means it is a final velocity. So it means it has the final kinetic energy, which is half mv square. So instead of writing this half mv square and half mu square, we can write this is final minus initial is equals to work done. Then we can say work done is change in the kinetic energy. That is change in the kinetic energy, because we are subtracting the final from the initial. So here we proved the theorem. Work done, whenever we will do the work done, the kinetic energy will change. But the question must come in your mind that the kinetic energy will change, but it will increase or decrease. So remember one thing, in the case when Ke will increase, when the Ke is increasing, so the direction of the force and direction of displacement will be in the same direction. So the work done will be positive. So whenever we are doing the positive work done, Ke will increase. And if the Ke will increase, that means velocity will also increase. This is the first case you must remember. Whenever the force applied in the same direction where the displacement is produced, so the velocity will increase. In the second case, when we apply, case second, when we apply force in the opposite direction where the velocity is being produced, so in this case, work done will be negative because theta will be 180 degree and the velocity will decrease. Always remember this. This is the two cases. But you might be thinking how it is possible. So best way to understand any concept is to go and check out in the numericals. Okay. So numerical is the best way to have a good grasp over the conceptual idea. So I'm going to give you a condition and we will try to find that how it is possible when positive work done we will do, then the velocity will increase. Okay. So I'm considering the first case. Let's suppose a body. Okay, this body is having mass. Suppose it is having 2 kg mass, and the velocity of this body is 10 meter per second. After certain displacement, okay, after certain displacement, the velocity of the body becomes 20 meter per second. The velocity becomes 20 meter per second. Okay, now we know work energy theorem says that change in the kinetic energy, okay, uh, is equals to work done, or the work done is always change the kinetic energy. So suppose this happens just within the 1 second. After 1 second, when I applied a force, when I applied the force of suppose we will take 20 Newton, then it produces a certain displacement, and the velocity becomes 20 meter per second. This is the final velocity. Okay, so if I'll prove this work done is positive. If the work done is positive, so the velocity will increasing. This will be positive also. Okay, so let's see this one. Displacement is in the same direction and the force I applied over here is quite simple. Now we will find out what will be the work done. So work done we know Fs. Okay, both are in the same direction. F is in the same direction and displacement also in the same direction. That means cos theta will be 0 here. This will be Fs. Okay. Now what will be the force from this? Now force is already given, or we can find out from here. We know force is nothing but an acceleration. So we will find the force is nothing but mass into acceleration. Mass we can put 2 kg. Acceleration we know change in the velocity upon time. Okay, so 2, and velocity is changing from 20 to 10 upon 1 second. So 2 into 10 it will be, that means it is coming 20 Newton. So I'll put 20 Newton. Okay, and what will be the displacement? So displacement we can also find out. The velocity is changing from 20. So we have the formula for the displacement. It is v square minus u square upon 2a. Okay. Now from a here we got which was coming 10. So first of all we will put the value of uv which was 20 square, and this will be 10 square upon 2 into 10. Okay, this will be 200 minus 100. Oh, sorry, it will be 400 minus 100 and upon 2 into 10. This will come 4300 upon 210. We can cut down this. So displacement is coming 50. So I'll put the displacement which is 15. Okay. So work done will be 20 into 15. It will be 300 joule. If I'll show that the change in the kinetic energy is also 300, then we can say this work energy theorem is correct. And the case one, which was saying when we apply the force in the same direction, where the displacement is produced, so the velocity is increasing. So if work is coming in the positive form, so change in the kinetic energy has to be in the positive form. That means the velocity is increased. Okay, so let's find out the change in the kinetic energy. Change in the kinetic energy will be uh, half mv square, which is the final velocity, and half mu square, which was the initial kinetic energy. Now see this one, half mass is 2 kg, v square we can take over here is 220 square, and this half 2 u square we can take 10 square. Now we can cut down this. So the value will come 20 square, that means it will come 400, and this will come 100. Now you see the change in kinetic energy also coming 300 joule. So this change in the kinetic energy also in the positive direction. I mean, it is coming positively, and work done is also positive. So as I said, case one was whenever we apply the force in the same direction where the displacement is producing. So in this case, velocity always increases. Okay, we can take the another example where the same case we will see and the velocity is decreasing. In the when it decreases, like I said, when the force applied in the direction opposite to the direction of displacement, then the velocity will decrease. That means the angle is over here is 180 and work done is negative. Okay, so we'll consider a case. Again, we are considering the same case. Suppose a body having mass m, okay, moving with a velocity of 10 meter per second. Okay, and after certain time, the velocity becomes 6 meter per second. Okay, now the velocity becomes 6 meter per second. Okay, what time we can take? Let's take this 1 second. Again, we will take, and the mass is 2 kg. Now here the velocity is decreasing. That means the kinetic energy Ki initial and Ki final. If I'll prove that the negative work done over here, the work done will be negative because they are acting in opposite direction, will decrease in the kinetic energy. That means decrease in the velocity. So the our condition will be also proved again. Okay, so I'm proving this one. Work done will be Fs. Now we're going to put the value F is mass into acceleration and displacement. S here we can take, okay, S here what we can take over here is cos 180. Okay, so cos 180 we are putting the values. This will be minus, and acceleration, what it will be, the acceleration, let's try to find out the acceleration. The final is 10, initial upon time, how much time is taken, 1 second. So it is coming 4. Acceleration is coming minus 4, and the mass will be 2 kg again, and this will come minus 180. And we have to find the displacement. So I'm going to find the displacement, which is v square minus u square upon 2a. Okay, so this v square, it will be 36, and this u square will be 100 upon 2a. A we know it is 4. Okay, so minus we can take over here. So this is coming 64. It will come minus 64 upon 2 into 8. Minus we can cut down. From this we can cut down 4 ones of 4 and 4 6 are 60, 24. This will be 8. So the displacement, you can see it is coming in a positive direction where the force is in the negative direction. Why? Because suppose the body is moving in this direction, suppose. So that displacement will also be in this direction. But we are slowing down the body. That means we have to apply the force. In this case, the force must be applied on a body in this direction so that the velocity will decrease and displacement is in this direction. So you can see force is coming, displacement is coming positive and force is coming in the negative direction. Okay. So here the displacement will be, I'm putting the value of displacement as 8 and this will come 8864 joule. This is the value of work done. Okay. Now, if I'll prove this, that work done is over here is decreasing the velocity, that means the change in the kinetic energy has to be negative. So I'm finding the change in the kinetic energy, which is initial kinetic, final kinetic energy minus initial kinetic energy. And this initial kinetic energy will be, final kinetic energy will be half mv square, and this will be half mu square. Okay, half m to v square. V is final what? 6, so it will be 36, and this half m will be 2 and it will be 100 because it is 10, so 10 square will be 100. We can cut down this. Again it is coming 36 minus 10, so it is coming minus 64. So we can say here the change in kinetic energy is actually in the negative. So that means the velocity will decrease. So always remember, whenever displacement and force are in the 180 degree, so the velocity going to decrease, and when they both are in the same direction, velocity going to increase. Hope you understood this. Thank you so much.